We are group 13. We are naming ourselves Bestla, and we are doing an autonomous parking project. We want to build an autonomous car that will park itself in a specific parking spot. Our time constraint was to build it in 800 hours with a budget of $200 to $500. The overall objective of this project was to learn how to use the depth camera housed in the Intel D435i and incorporating this into our image processing. We also wanted to further our knowledge with OpenCV, specifically through Python. We put all of our code in. The central hardware device was the Raspberry Pi that's housed on the chassis of the car. And we also wanted to appreciate self-driving cars in that new technology. So for our problem definitions, we wanted to know how to create a self-parking autonomous vehicle. So looking at the components such as the chassis and how we were going to control the movement of the wheels. We also needed to take a look at the hardware and software that we would be using and what operating systems we would use just to make sure everything would be compatible with each other. And we also wanted to learn how to use computer vision to identify a parking spot. The goals that we set for the final model of the project was to have 95% accuracy on whether the car can park itself in the correct spot on the left or on the right, whether the car can detect parked cars and avoid those parking spots, and if the car can park within the lines of the parking spot 90% of the time. The app can also connect to the car and the user chooses which parking spot the car will park in, and then the car should be able to park itself in an open spot.
This is a block diagram of our project that really just shows the relationship between our pieces of hardware. We use the Raspberry Pi Model 4B at the center of everything. And this was interacting with our app, the motors on our smart car, the servo to turn the camera, as well as the Intel depth camera.
Here you can see our car and our model parking lot in which our car will have to try and find a parking spot.
So for our hardware design, our car is powered by 2 lithium-ion batteries, each 3.7 volts that are wired in series. So the input voltage ranges around 7 to 8 volts. And the Raspberry Pi is powered by these 2 batteries. And the Raspberry Pi is powering the camera and the servo motor with an input voltage of 5 volts. And the Raspberry Pi also is powering each wheel of the car. And each wheel is running off of a separate motor at a rated voltage of 6 volts and 150 milliamps of current. The duty cycle on our car is 12%. And looking at the pictures below, we have the top of the car on the left side and the bottom of the car where the batteries and the motors to power the wheels.
So this is our flow of our software. So first, our program will wait from input from our Bestla app, which will be either them picking a commuter, employee, or handicap spot. And then our program will start and it will look at first the left parking spot, and it will do some image processing and determine if that is the spot that was desired from the app. If it is the spot, then the car will turn left 90 degrees. And then it will use the depth camera to determine how far the car is from the wall, and using that information, it will drive forward into the spot, and then it's parked and the program ends. However, if it's not the correct spot, or if the spot's already occupied, then the camera will then spin to the right to see the parking spot on the right side of the car, and it will again determine what kind of parking spot it sees. And again, if this is the correct parking spot, it will turn right, it will determine how far the car is from the wall, and it will drive into the spot and the program will end. And if again, it's not the spot, then it will make a decision if the car's at the end of the lot or if it can still go one space forward. So if it can go one space forward, it will do so, and it will repeat the process over. And if not, then it will be determined that there are no spots available in the lot and the program will end.
And so here is our Bestla app that we use to determine which spot we want to choose. So this is an iOS app, and as such, it was designed with Xcode as the integrated development environment and programmed using Swift programming language. It uses Cocoa MQTT as the library and framework for using the MQTT messaging protocol. And that's how it talks with the Raspberry Pi and tells it which parking spot to choose. And as you can see here in the blue is the input in which the user inputs to the app, things such as the IP address of the MQTT server and which parking spot we want to choose. And then in the red is our status box, which is the information output by the electric vehicle. And so integration with the Raspberry Pi uses MQTT like mentioned before. The app publishes to the Bestla/spot topic to tell which spot to look for, whereas vice versa, the Raspberry Pi will publish to the Bestla/status topic with information about the current status of the vehicle. Here is a demo of the application. So first I connect to the MQTT server, and then I subscribe to the status topic, and then I indicate to the car that I want to park in the commuter spot. Fast forward to once the car has found that spot and has parked in it. As you can see here, I adjust a parameter to adjust the way the car is driving. And you can see that the car is parked and has sent a status back to the application telling it has parked. And the application has published or has sent that status to the status box, letting you know. And so now I want to tell it to park in the handicap spot. First I have to clear the status box, and I click the handicap spot, and you can see it's then published to this Bestla/spot telling the car where to park. Fast forward again to once the car is parked, and it again tells the status to the application, and the application lets you know.
For color recognition, we got the data from the Intel RealSense camera and stored this data in an array in Python that had the 3 RGB values, and these values were used to distinguish between white, blue, green, and orange, which would determine which of the signs was placed at a designated parking spot. And these different parking spots are shown in the images below. We had handicap, which is blue, commuter, which is orange, and employee, which is green. For the depth readings, we use the LiDAR camera housed in the Intel camera to get them, and all of the data that was obtained was stored in a Python array, and all of the measurements were in millimeters. We used these readings to determine how far away the car was from the end wall of the parking lot, so that when it turned left or right at the spot it was supposed to park at, it would calculate how far the front of the car was from the wall so that it would pull up into the spot the right distance.
So now we will show some of our methodology and the results of that. The 2 main things we had to troubleshoot and work on for this project was the movement of the car and the color detection. Originally, the movement was very inconsistent, and we solved this by adding some real-time feedback. Before, for our color detection, our RGB values varied a lot and they were far from the actual values. And we fixed this by still taking an average value, but by throwing out the white pixels. This graph shows how inconsistent the car moved. The orange bar is the first trial and the purple bars are the second trial. And for each trial, we did times ranging from half a second to 2.5 seconds. And we did 3 attempts at each trial. And as you can see, even within each trial, the car moved a different amount of centimeters, with the largest range being 8 centimeters. And in between the 2 trials, between the orange and the purple, you can see that the car sped up, even though the trials were only 5 minutes apart. This graph shows how our RGB values improved from before throwing out white pixels to after. The black bars are the actual RGB values, the orange is before, and the purple is after. For the commuter orange signs, every single RGB value got better. For the employee green signs, 2 out of the 3 RGB values got better and closer to the actual values. And for the blue handicap signs, 2 out of the 3 RGB values improved.
So for the strengths of our project, we looked at parking sign recognition and depth detection. After multiple trials, we determined that each of these had about 95% accuracy. And for the weaknesses of our project, we saw that the car had some inconsistent movement, which happened when we would run the same program and the car would either go too far, not far enough, overturn or underturn. And we solved this with manual feedback in our app. Another weakness was our battery charge only lasted about 2 hours, so we'll have to constantly recharge them. For our project, we ended up meeting most of the goals that we set forth at the beginning of the semester. We were not able to implement parallel parking or reversing into spots, and this was due to the car being differential drive. But we did learn how to use Xcode and Swift, and we learned how to work with the Intel RealSense camera and OpenCV in Python. And so we were able to further our knowledge in Python and MQTT.
Okay, and now here is a demonstration of our final product. So first here, we wanted to get our car to park in this commuter spot on the left. As you can see, it's scanning the spots and finding cars in these spots, so it's not parking there. And then it parks in this commuter spot, but we realized that our car did not move up far enough, so we manually edited some of the parameters for tuning the way in which it drives to make it drive a little further. And so in this next clip, we want to park in the handicap spot, and you'll see that it parks a little bit better because of the tuning that we did and tuning those parameters to make it more reliable and more consistent. And then up here on the right, it parks in this handicap spot. And that's our project. Thank you guys for watching.